G minus. So current comes in from the front of the block on the right, being pulled off the right rail, flows across these contacts, G plus, G minus, goes through the rheostat, R2, and onto the on-off block.
Hello, I'm James Ingram. This video was digitized from a 1992 videotape series named V9202.
There's a series of 7 drawings that accompanies the documentation to reconstruct one of these optical blocks. It's laid out very similarly to in structure to the 7 drawings for the magnetic block. Sheet 1 of this drawing set is the assembly drawing, which shows the parts, gives the dimensions to locate parts, and the part numbers of what's shown on the drawing. Then you can see that on the top part of the page here is what I've been referring to as a track unit. On the bottom part of the page is what I've been referring to as the control unit. Sheet 2 of this set is the wiring diagram that shows again the track unit and the control unit, this time with all the wires shown on it necessary to connect the unit up. And again, there's a wiring color code. And I've tried to be semi-consistent with all the different drawings that have been made for these automatic control items, the magnetic block, automatic block, and the automatic switching system. Basically, red and yellow are used for AC inputs, red being AC plus and yellow being AC negative. The color green is used where there's an AC line that's switched, i.e. it's not always on, it's on or sometimes off. DC wires are the heavier lines. Blue is DC wires that are essentially unswitched, and then black is used for DC wires that are switched. That is, again, to say turned on and turned off sometimes. Sheet 3 of this set is a schematic diagram that just shows the same wire identifications as the previous wiring diagram, but tries to do it in schematic form, so it's a little easier to follow. Sheet 4 is a page full of explanatory notes. And sheet 5 is another bracket detail for the rheostat mounting bracket. Sheet 6 is an installation drawing that just shows you how to mount one of these things in a loop of track, basically. Then sheet 7 is our parts list and cost estimate. This is basically just a list of all the parts necessary to create one of these optical type blocks. Again, using Walther's catalogs and Radio Shack catalogs, plus the stated price for the APS electric eye, the cost of all the parts for this thing would be in the ballpark of $261. And just throwing in a rough estimate of around 31 hours of labor at $5 an hour, your invested labor cost needs to be about $155 for a grand total of somewhere around $416 for an assembled unit. And again, these prices aren't exact because these, as you know, these train parts are always moving around in price. Let's go back and take a little closer look at that sheet 3, the schematic drawing, which was divided into 4 parts. Looking at figure 3.1, this one says heavy lines show AC current flow when the block is in the red state. AC current flow for the red state. The clear, non-colored power indicator light is always lighted. When the block is red, current flows to the normally open yellow contacts to light the red indicator light. Here's the clear indicator light here and the red indicator light here. So this, as mentioned, this red indicator light is always always on if assuming the knife switch here is closed and the block is powered. When the block is in the red state, that's when the eye is activated. The path basically is down through here to the this is the path that actually power the block. The yellow contact points are shown up here. They're actually on the block here, but to make the drawing clearer, those same 2 points are shown here as Y minus and Y plus. This is Y minus here and Y plus, but the wires are actually shown up here schematically. So the path through that basically is coming in here, down here, across to the Y minus side and across the Y plus side and up to the other side of the light. So that makes the red indicator light go on when this thing is in the red state. Now let's take a look at figure 3.2. It says heavy lines show DC current flow to the track when the block is in the red state. The previous sketch up here was for the AC current flow in the red state. This sketch is for the DC track current flow when the block is in the red state. It says DC current flow for the red state. When the block is red, the normally closed contacts G plus, G minus are held open. Current for the right rail does not flow to the on-off block. It comes in via wire such and stops at the open point. And current to the slowdown block flows through the path such and such. Let's look at that. Basically, here's your well, first of all, here's your block outlined kind of in the gray. That's the block itself. So in front of the block is the what I refer to as the mainline trackage, where the block doesn't have any effect. Behind the block, and again, notice travel direction is from left to right, shown by the little locomotive. Behind the block is the slowdown block. So when the block is in the red state, these contacts G plus, G minus, the green terminals, which again on the block physically are about here, but they're shown, the wire connection is shown up here, kind of schematically for better clarity. These are open. They're normally closed, but since the block is in the red state and activated, the contacts, green contacts G minus and G plus, which are normally closed, are now open. So there's no path to the on-off section, and it's open because this contact is open. There is a path to the slowdown section through the rheostat R1, which is shown by this heavy black line, which is what we expect. When the block is activated to the red state, you get partial voltage to the slowdown section, the partial voltage being controlled by the adjustment of this rheostat R1. There's a diode here which prevents the DC track power from going back to the on-off section. This only has one set of contacts that are normally closed, as opposed to the magnetic unit uses the 1203 points, which have two sets of contacts. So due to having to control two blocks with the one set of contacts, it kind of had to double up, and that's why this diode appears in this optical unit, and you don't find any diodes in the other units. There's a little bit of just working around the fact that there's only one set of contacts. We'd really like to have two sets of contacts on this unit if we had our others, because we'd use one set for the on-off block and one set for the slowdown block like we do with the magnetic unit. But since there's just one set of normally closed contacts, we've got to use this diode and kind of double up. Let's go look at figure 3.3, which is the AC current flow when the block is in the green state. We looked at AC flow when the block was in the red state on figure 3.1. Now this is what happens when it's in the green state. Over here it says AC current flow for the green state. The green power indicator light is always lighted. That should read clear. This light used to be green at one time. I haven't gotten all the references out of that. The clear power indicator light is always lighted. The red indicator light is not lighted. So basically there's just two paths for AC current. Again, here's a knife switch. You've got one path going down to the red and black terminals that actually power the eye control unit, and your other path just is into the clear power on indicator light. That's the only AC current flow you see in the block when the thing's in the green state. Now let's look at DC current flow to the track when the block is in the green state. That's figure 3.4. It says heavy lines show DC current flow to the track when the block is in the green state. DC current flow for the green state. When the block is green, the normally closed contacts G plus G minus are closed. Current for the right rail flows to the on-off block via wires D1, D2, terminal G plus across terminal G minus and on through some more wires. Current to the slowdown block flows via the stated path. Let's look at that on the sketch. Again, here's the block, the main track in front of the block, the slowdown section to the rear of the block. In the green state, both the on-off block and the slowdown block are getting voltage. The path, since these normally closed contacts are closed for the block being in the green state, there is a path from G plus across to G minus, so current comes in from the front of the block on the right, being pulled off the right rail, flows across these contacts, G plus, G minus, goes through the rheostat R2 and onto the on-off block. And again, as I mentioned with the magnetic block, you do have a minor unwanted side effect that when the block is green and an engine goes across it, you still get a slight slowing down due to the rheostat R2, which there's no easy way to avoid this without some super complicated circuitry. Voltage or current also goes to the slowdown block via this path here after it goes across the contacts G plus, G minus, and before it goes to the rheostat R2, there's a connection through the diode, so the current can flow in the forward direction through the diode to the slowdown section. So the slowdown section essentially is getting full voltage in the when the block is in the green state. There may be some current going through this path here through rheostat R1, but since the diode in the forward direction should have relatively little resistance compared to this rheostat, the bulk of the current flow should be through this path. These labels on these schematics, and incidentally, when I say labels, I mean the wire names, for example, D11, D10, D9. These are consistent between the schematics and the wiring diagrams. For example, if you follow this path on this schematic, figure 3.4, it shows current exiting the terminal G minus, going on wire D11 and then wire D10 to get the rheostat R2, and then exiting rheostat R2 on wire D9. Now if we look at the actual wiring diagram for that same area, coming from the terminal G minus, which is right here, here's wire D11, we can see it goes over to the terminal block, and then via the terminal block it goes on wire D10 over to rheostat R2, exits rheostat R2 on D9. So and likewise all the other wire labels should be consistently the same way. These small numbers behind the labels, which appear behind all the wire labels, like are suggested cutting lengths, like D9, it says D9 parentheses 17 inches. That just says it's a suggested length to cut that wire 17 inches long to use it initially, and it should include a couple inches for margin of error. You can see though that it's harder to follow the current paths through this wiring diagram, which is the reason why the schematics were created. The schematic shows essentially the same wires, the same current flow. It just tries to make it as easy to follow fashion as possible.